All right, good afternoon, everyone. It's been a week since we've been together, so hopefully you've had a good amount of time to study, catch up on homework, anything like that for the first two sections. As I said, I didn't have a due date in for the third section since we're still working on it for now, but we will finish that today, so it will be due in a week, which would be the 16th. So I still need to edit that in my math lab, but I will do that as soon as this class ends today. And I mentioned that usually at the top of each class, I'm going to have a little, if we were doing this in person, I would put a few things on the board to the side for us to reference all day long. So I just have an extra document I'll call my board cheat sheet. And today it looks like this. Another day it might look a little different. But I suggest that you kind of have one of these to the side for your own notes, because this is just things that are very helpful to have. And when you take a test, this is something that you could create once you start the test. This is not a document you should have before the test. This would be something that, all right, the test is starting on a blank piece of paper. Let me write SOHCAHTOA down to help remember sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. Your reciprocal functions, your Pythagorean identities, those two base triangles. Also, you might want to mention somewhere that pi over 6 is 30 degrees, pi over 4 is 45 degrees, pi over 3 would be 60 degrees, and others if you felt like you needed that. But again, that's stuff that you would write down once you started your test, not before, not before, not before. These are not open notes tests. Then I have a smart trig class, which helps us to remember all, sine, tangent, cosine.
Mr. Beckner?
Yes.
I can see your screen, or I can hear you talking, but I can't see your screen.
You know what? Zoom has done this to me a couple of times now. If I have it loaded, it doesn't set me up correctly. Boom. Thank you for catching that. Okay, so very quickly starting fresh. Hi everyone, this is what I was just referring to, the little board cheat sheet, which again, sometimes I'll have extra things on here, sometimes I won't, sometimes might have less of this up here. It's more about what's relevant for the day, and we won't use all of it necessarily. But your SOHCAHTOA, your reciprocal trig functions, let me not say inverse, that would have been wrong. Your Pythagorean identities, your 45-45-90 triangle, your 30-60-90 triangle, a couple of quick radian to degrees conversions that we see constantly just to get used to. And this is something I won't write anymore after a week or two. Then the last thing that we did, which was developing how to find the trig function of an angle outside of the first quadrant, so no longer restricted to a right triangle. Because we said that we use these reference angles and then it just might have a negative half the time. And it turns out that the patterns, based on the fact that sine goes like y over the radius, cosine x over the radius, and tangent the ratio of y over x, because that would be sine over cosine, that all of these are positive in quadrant 1 because all of the x and y coordinates are positive. Sine is the only positive one in quadrant 2 because you're going up and sine relates to y. Tangent's the only thing that's positive in quadrant 3 because sine and cosine were both negative and that ratio would be positive. And then cosine's the only thing positive in quadrant 4 because you're going right and down. So a smart trig class helps you remember they're all positive in quadrant 1, sine's positive in quadrant 2, tangent's positive in quadrant 3, cosine's positive in quadrant 4. Remember, I don't care how you're going about memorizing and using things, I just care that you have a system that works for you that is legitimate. So that's why I've given you both of those versions. And then the last thing that I want to do before actually continuing into 7.3, you don't need to see my virus notifications. Before we continue into 7.3, I believe this actually goes back to, and I said 7, I meant 5. I told you I'm going to keep doing that. 5.1? Yeah, it's 5.1. Oh, just not over my notes. So converting between normal degrees and then a degrees, minutes, seconds system. So this is just going to be something that you'll see in the homework, not on the test, but it's something that you could come across in another class that involves trigonometry. So I still want to make sure you have this methodology, but it's converting between decimal degrees and degrees, minutes, seconds. The idea is all about multiplying or dividing by 60. That's all it is. So if you're starting in degrees with decimals, so something like 3.5 degrees, what you will do is to get the minutes and the seconds, multiply the decimal value by 60 to get the minutes. Then, if this number has a decimal, multiply it by 60 to get the seconds. That's it. That's all it is. So if you're starting in decimal degrees, something like 1.52. So 1.52 is what I'm starting with. What you do is you take the decimal value of 0.52. So 0.52, and you multiply it by 60. That gives you your minutes because there's 60 minutes in an hour. So the degrees are kind of like your hours. So 31.2 is the minutes, but we're trying to avoid decimals. So now we take this decimal value. So 31 will be the real minutes, but the 0.2 will give us our seconds. So now what we have, let's see if I can just do this. So we had 1.52 degrees. We multiplied the 0.52 by 60 to get 31.2 minutes. But then we take the 0.2 and multiply it by 60. And that'll give us 12. So that means it's 12 seconds. So that means this is really 1 degree, 31 minutes, and 12 seconds. Going the other way, starting in DMS, degrees, minutes, seconds, take the seconds and divide by 60. We're just doing the opposite, basically. And add this to the minutes and divide by 60. So let's work backwards. Let's take the 1 degree, 31 minutes, 12 seconds. Let's take the 12 and divide it by 60. And we get 0.2. 12 divided by the 60 is 0.2. Add this to the minutes. So 31.2, then we're going to divide that by 60. 31.2 divided by 60, and you get 0.52. That's your decimal. So the original number, 1D, 31 minute, 12 seconds, would be 1.52. The same thing we originally had. And that's degrees, of course. This is not something you will ever see me do in class again. But there are certain schools of thought, if you will, that prefer degrees, minutes, seconds over just a decimal value for degrees in general. So they'll go and do that conversion. Maybe if you're an engineer and you want just a little more specific accuracy, it doesn't really make it more accurate technically, but it just might make it more relatively accurate to their own system. So again, you'll see 1 or 2 of these in the homework. You're not going to see it on the test. It's not something you have to master, but I still wanted to introduce it because you might come across it at some other point, and at least you've seen it at one point in your life. seconds. So that's our degrees, minutes, seconds. Oops, wrong button. So here's our board, our whiteboard that we'll pop back over to every now and then. But for now, let's go back to 5.3. So again, the last thing we developed in 5.3 was a smart trig class talking about the SIGN pattern of your three main trig functions in the specific quadrants 1, 2, 3, and 4. We developed this because any point in quadrant 2, 3, or 4 can be made a relative point in quadrant 1 just by changing the signs of their x and y coordinates. So a reference angle, the theta prime, can always be found based off of an original angle, and their two trig functions are the same except maybe a negative of one versus the other. And we're going to go over how to figure out what the reference angles are and how to use them coming up. All right, so example 1. If the sine of theta, I'm going to write the theta in just a moment, is greater than 0, the cosine of theta is less than 0, which quadrant must theta be in? So if the sine of your angle is positive and the cosine of your angle is negative, which quadrant must the angle be in? So we're going to learn how to tell this. Now you have to be given two conditions. You cannot tell the quadrant just based on one, because if I just tell you sine's positive, well, sine's positive in quadrant 2 and in quadrant 1. So you could not tell me which quadrant it would have to be in. You could say it's in 1 or 2, but I'm not sure. So that first condition, if sine of theta is positive, that says we have to be in quadrant 1 or in quadrant 2. And again, the reasoning behind it is sine is tied to y. Essentially, y is going up in quadrants 1 and 2, which makes it positive. So the first condition says it's in quadrant 1 or 2. We're not sure yet. Second condition says, all right, the cosine has to be negative. Cosine's tied to the x value, and we want the cosine to be negative. X's are negative when you go left. So cosine's negative in quadrant 2, and cosine's negative in quadrant 3. Now I'm doing the rationalization using the coordinates x and y, but you also could just do this all based on a smart trig class. You can draw this up all by using ASTC. I even did it a little more color-coded on the cheat version of the board. Wrong thing. See, I color-coded it. The positives are blue. All, sine, tangent, cosine. A smart trig class. Then that just makes the rest negative. So the second condition, cosine is negative, says we were in quadrant 2 or in quadrant 3. Well, you just got to make it happen in both. So the first condition says we're in quadrant 1 or 2. The second condition says we're in quadrant 2 or 3. Take the overlapping one. Thus, theta is in quadrant 2. That's it. You just got to make sure both conditions are upheld. It can't be in quadrant 1 because the second condition fails. It can't be in quadrant 3 because the first condition fails. And that was example 1A. I forgot my A. A. B, if I hit enter, it'll screw everything up. Sorry for that. Oh, that's too low. B. All right. If the sine of theta is less than 0 and the tangent of theta is less than 0, which quadrant are we in? So if the sine of theta is negative and the tangent of theta is negative, what quadrant are we in? So these are the two conditions. Condition 1 says, well, the sine has to be negative. Sine goes like y. So whenever the y's are negative, when the y's are going down, we're going down on this. So down puts us in quadrant 3 or 4, and this confirms it. Sine is negative in quadrant 3. Sine is negative in quadrant 4. Each of these are split 50-50. So quadrant 3 and 4. So by condition 1, it's quadrant 3 or quadrant 4. The second condition, I didn't mean to switch my numbering that time. The second condition was that the tangent has to be negative. So we can go back up to this. Where is tangent negative? Tangent's negative wherever the ratio of your coordinates is negative. Or you can use a smart trig class. So tangent's positive in quadrant 1. It's negative in quadrant 2. Oh, there's one of them. So quadrant 2. It's positive in quadrant 3, so that's out. And it's negative in quadrant 4. So we're either in quadrant 2 or we're in quadrant 4. So the second condition says we're in quadrant 2 or quadrant 4. What's the overlap? Quadrant 4. Thus, your angle, theta, is in quadrant 4. We're not finding any sines or cosines or tangents of these larger angles yet. We're not up to that point. We're getting close. We're getting very close, but we're not there yet. All right. Let's try out something kind of similar, but let's beef it up a little bit. Example 3, excuse me. And for A, given that the sine of your angle is equal to negative 3 over 7, and the cosine of the angle is negative, let's find tangent of the angle. Remember that second section, excuse me, 5.2, we were restricted to a right triangle. We were restricted to angles between 0 and 90 degrees. We only established sines, cosines, and tangents for 30 degrees, 45 degrees, and 60 degrees. Yes, they exist for all sorts of other angles in between. We didn't establish them. Now we are in the whole entire 360 degrees or 2 pi full circle, any quadrant, not just quadrant 1 from 0 to 90 degrees. We're thinking quadrants 1, 2, 3, or 4. So the sine of the angle is negative 3/7. This ratio of 3 to 7 is going to help us find the third missing side if we were to call this a right triangle. And then we'll be doing a tangent of that. But because we can be in any quadrant potentially, we now need to know whether these things are positive or negative, and we have to have two SIGN sign conditions to be able to pinpoint that. Without this second condition, if the sign is negative, that means we're going down, that means we're in quadrant 3 or 4. But you can't tell me the tangent of it because you don't know if you're in 3 or 4. The answer could be positive something or negative something. It depends on whether you're in quadrant 3 or 4. So that's why we needed the second condition that I temporarily scribbled out. All right, so if you draw up a reference triangle, first, which will look like this. So this is not going to be the angle, this would be the reference angle. So this will be theta prime. Now the sine is negative 3 over 7. Sine is SOHCAHTOA, S-O-H. So that's opposite over hypotenuse. So the opposite is supposed to be the 3. Now I'm drawing this as a right triangle, so writing it as a negative might throw you off. So I'm going to do it as a positive. It's up to you if you write the negative. It won't matter ultimately, but let's just see what happens. And then the hypotenuse is supposed to be 7, which means we can find this side, if I label it as A, by Pythagorean. We can say that A squared plus 3 squared is equal to 7 squared. Or A squared plus 9 is equal to 49. So going down here, that says that A squared is equal to 40 if you subtract 9 on both sides. And then when you take the square root of both sides, you'll get the square root of A squared is equal to the square root of 40. But we can simplify the square root of 40. So we get A equals the square root of 40. But we can break up 40 as a product, 4 times 10, because we know the square root of 4. You wouldn't want to do 2 and 20 because you don't know either of those square roots. Whoops, sorry for that erasing. This pen is wacky sometimes, which gives us 2 square root of 10. The square root of 4 is 2, so that popped out. The square root of 10 stays. So that's the A. That is the adjacent side to the reference angle. Now that we have A, which is the adjacent, we could be able to find tangent with one extra feature. Tangent's supposed to be the opposite over the adjacent, so it would be the 3 over the 2 square root of 10, but maybe it's positive, maybe it's negative. It depends on the quadrant. So we said the sign was negative. Since the sign is negative, we're in quadrants 3 or 4. The same statement we said before based on a smart trig class. If the sign's negative, you have to be in quadrant 3 or 4 because you're going down. So that's what the first statement says, in addition to saying that the ratio of the opposite and hypotenuse is 3 to 7. It also says we have to be in either quadrant 3 or 4. But they also told us that the cosine of whatever angle we're finding or dealing with is negative. Cosine being negative means, let's just do the colon, we are in quadrant. So cosine relates to x. X is negative when we go left. And you go left, you hit quadrant 2 or 3. And again, I'm doing the rationalization based on the x and y coordinates of going left, right, up, or down, but a smart trig class finds all of that out for you as well. Pick your poison. So cosine being negative says we have to be in quadrant 2 or 3. What's the overlap? Quadrant 3 or 4, quadrant 2 or 3. Thus, our angle is in quadrant 3. So these 3 typed out sentences, statements, whatever, are what we were doing in example 2. But now we've thrown example 2 into the mix, and we're actually trying to find a trig function of said angle. So we know we're in quadrant 3, and we're finding a tangent. We're trying to find the tangent of that angle. Quadrant 3, tangent, a smart trig class, T, positive. So tangent's positive in quadrant 3. So when we do the ratio of our opposites, adjacents, hypotenuses, whatever it is we need, we just got to make sure the answer is positive and we're good to go. That's why I don't really traditionally label these as positives and negatives in these right triangles. First of all, it's kind of misleading because in geometry we can't have negative sides. But I also understand if you were drawing this triangle in its relative position that you'd have a -3 because it'd be pointing down. Also, the A ultimately would have been negative as well because we'd be pointing left. So again, this A is for the reference triangle, not the actual coordinate. It would be -2 square root of 10 because we're going left and down to get in quadrant 3. See here, our angle has to be in quadrant 3. This right here is our theta, which means we're going left and down. So if you drew that reference triangle in there, it would look like this. -3, that's the vertical distance. -2 square root of 10, that's the horizontal distance. And then 7 was the radius, if you will. And then this right here would be your theta prime. Sorry, that's a little small. I'll zoom in for a second. More in a second. Again, this is drawing the reference triangle in its relative position to the original angle. So now the terminal side is exactly where it would have been before. But you don't have to do things that way. Again, I'm showing you alternate ways of doing things because some people like to do them alternate ways. Okay, so finally, the tangent of theta. That's going to be its opposite over its adjacent, where the opposite was the 3, the adjacent was the 2 square root of 10. Now we know tangent's positive in quadrant 3, so this is definitely a positive. If we were in quadrant 2, let's say that for some reason we were in quadrant 2, all I got to do is just make sure I slap a negative on this. Now, if you are doing it this way, all of the signs are correctly in place and you would see the negatives cancel to get this, but I just find that most students don't, or they miss a negative somewhere. So I do think that it's important to understand this as a whole. And unfortunately, this is not an acceptable answer. You have to rationalize the denominator. So you don't have to multiply by the 2, just the square root of 10. You only multiply by the radical part. So you get 3 square root of 10 in the top, over 2 square roots of 100 in the bottom. But the square root of 100 is 10. So that's 3 square root of 10 over 2 times 10. 2 times 10 is 20. So 3 square root of 10 over 20 is our answer. That is the tangent of the angle. I know that seems like a lot to balance all at once, but you will be doing these over and over and over and over and over. This is not going to go away as long as we're doing trigonometry in this class. Did it matter that I set up the reference triangle first and then talk about the sign SIG ends? No, I could have talked about the SIG ends first and then done the reference triangle. The order of these two ideas doesn't matter. You just have to do them both so that you can actually get to this. And again, we made sure this was positive because we're in quadrant 3, so the tangent would have been positive. Let's say, for example, the problem asked me to do the secant of the angle. I'd have to say, well, secant and cosine share the same sign, so it would be negative because we're in quadrant 3. Cosine's negative in quadrant 3, so its secant would be negative. So then I'd have a negative, and then the ratio of opposites, adjacents, hypotenuses, whatever it is. So very common type of problem. That was that little memo for myself reminding me to do DMS last time. Let's try another. So B, given that the sine, as much as I can for now, let me back out one layer, there we go. Given that the sine of the angle is equal to -2 over square root of 11, I'm just going to write the rest. It's tedious otherwise, and the tangent of the angle is negative. And I don't have to write it this way. I could spell out tangent is negative. Find the cosine of the angle. So this is what we're ultimately trying to do. We're trying to find the cosine of the angle. We're not finding the angle. We did not find the angle in example A. We're not finding it in B. It's actually quite difficult to do that way. My 2 up here looks a little silly, so I'm going to fix that. There we go. All right, so last time I drew the reference triangle first. Let's do the sign issue first this time, the plus or minus sign aspect. Also, you might be saying, Mr. Beckner, you left a square root in a denominator. How dare you? I did that for your benefit. because we haven't seen enough of these yet to kind of know what things will look like when the square root's in the top and not the bottom, but we'll get that habit ultimately. So for now, I'm actually doing you a favor right now. So this time we'll do the reference triangle last. Let's go ahead and discuss all of the, why is it not letting me click anywhere lower? That is weird. Word, you're weird sometimes. Okay, so let's do the quadrants. This says sine is negative. So since sin is negative, that means we're in quadrant 3 or 4. Sine goes like the y value of a point. They're negative when you go down. Going down means you're in quadrant 3 or 4. Tangent being negative means we're in quadrant. Let's see, tangent's negative in quadrants. It's positive in quadrant 1 because they're all positive. It's in quadrant 3, a smart trig class, T is quadrant 3. So that means if it's positive in quadrants 1 and 3, it's negative in quadrants, you guessed it, 2 and 4. 4, 4. And or the wording doesn't matter. Thus, our angle is in quadrant. What's the overlap? 4. To the side, I'll do our reference triangle. Reference triangle, let's abbreviate that out. So the sine is opposite over hypotenuse. So the opposite is 2. The hypotenuse would be a square root of 11. So it doesn't matter what direction you draw your reference triangle unless you're actually putting it in quadrant 4, in which case you'd be pointing this down, but that's not what I'm doing. So here's our reference angle. This is not the legit angle, that's the reference angle, with an opposite of 2, ignoring the pluses and minuses, and a hypotenuse of square root of 11. This makes the third side, A, easier to find by Pythagorean. So we would say a squared plus 2 squared is equal to the square root of 11 squared, which is a squared plus 4 is equal to 11. Subtract 4 on both sides. That tells us that a squared is equal to 7. Take a square root of both sides, and you'll get that a is equal to the square root of 7. I skipped a couple of steps showing them, but you should all know how to solve that Pythagorean equation by now, I hope. So that says the adjacent is square root of 7. There's actually 2 radicals in this right triangle. Nobody said they couldn't all be radicals. Nobody said they had to have a whole number anywhere. It's nice when they do, but they don't have to. So now we can finally find cosine of the angle. We can find the cosine because we know what quadrant we're in, so we know whether to attach a plus or a minus to this at the end of the day. And we also have the opposite, adjacent, and hypotenuse to find that correct ratio. So the cosine of theta should be equal to, and again, cosine is ca, C-A-H, adjacent over hypotenuse. The adjacent being the square root of 7. The hypotenuse being the square root of 11. And then I'm going to write a symbol here temporarily. It's a matter of which one do we choose? Do we choose the plus or do we choose the minus? This is not the plus or minus from the quadratic formula or the square root principle. I'm saying it's going to be an either or scenario. It's either plus or minus based on the quadrant. How do we know? We're in quadrant 4. Cosine is going to be, is it positive or negative in quadrant 4? A, smart, trig, class. C, cosine's positive in quadrant 4. If you don't believe me, cosine's positive. That's because we're going right. Cosine goes like the x value. So I'm actually going to leave this in here and say that it's quadrant 4, cosine is positive in quadrant 4. So this is going to end up being just square root of 7. Why did I leave that space there? Square root of 7 over square root of 11. And if you circle this, this is what's going to happen. It's wrong. Because there's a square root in the bottom, not allowed. But Mr. Beckner, you had it in your original problem, but that doesn't mean it was technically correct. Again, the sign, I really should have multiplied top and bottom by square root of 11 and gotten -2 square root of 11 over 11, but it would have made the Pythagorean calculation a little bit more of a pain. So again, this was in an incorrect form just to give us a little push. But our answer does need to be in the correct form, so we have to multiply top and bottom by square root of 11 to fix it. And we will get the square root of 77 in the top over the square root of 121 in the bottom, which is the square root of 77 over 11. If you skip the middle step and just say square root times square root is the whole number of 11, that's fine with me. But there's our answer. If for some reason our angle had been in quadrant 3, then this would have been a negative answer. That's the only difference there. So the first time we did the reference triangle first to find the missing side. Then we did the plus minus sign patterns. This time we did the plus minus sign patterns, and what I mean is SIGN patterns, then the reference triangle. Doesn't matter the order you do those two things. It matters that you do both of those. So here's what happens on a test. Nobody wants to do this plus or minus thing and figure out which it's supposed to be. So they just pretend everything's in quadrant 1 and they make all their answers positive and they get half of them wrong because of that. And that's a major problem. You have got to go through both of these ideas. This is the number one type of mistake students make on this first test, is they don't do this stuff right here, figuring out what quadrant you're supposed to be in, as well as picking an appropriate sign based on that quadrant, plus or minus sign, that is to say. Okay, so we keep talking about this reference angle and how we can use it to find trig functions. And we have basically been doing this right here without actually doing it. But how can we go from, say, an original angle of maybe 210 degrees to a reference angle of 30 degrees for that one in particular? How would we go from a reference angle of, say, 301 degrees, I'm sorry, I said reference there. How could we go from a regular angle of 301 degrees to a reference angle of 59 degrees? Or how could we go from an actual angle of 120 degrees to a reference angle of 60 degrees? That's what we want to focus on now. Converting to a reference angle. Not just drawing up the triangle and leaving it blank. If you know the original angle, we can now find the reference angle. There's three scenarios. You're either in quadrant 2, 3, or 4. Because quadrant 1, you don't need a reference angle. In quadrant 1, the reference angle is the angle. So when you're in quadrant 2, so here's your terminal side. Here's the point at the end of the terminal side, if you will. So going from here to here, swinging this way, that's our true theta. But this right here would be our theta prime. As a reminder, a reference angle must always swing from the x-axis. I'm going to scroll up to show that. A reference angle is the angle from the closest x-axis to the terminal side. You must always swing from the left-sided horizontal axis or the right-sided horizontal axis. You're never considering yourself swinging from a y-axis. You will never, ever, 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 ever see me put a reference angle here. If I put my reference angle here, read for wrong, because that's going between the y-axis and the terminal side. So that would be wrong. You have to swing from the x-axis. So when you're here, you're somewhere between 90 and 180 degrees for your actual angle. Going here, this might be 120 or 135 or 150 or 179. Your reference angle's got to be between 0 and 90. Well, the whole thing would make up 180 degrees. If you cut off the angle, that would give you the remaining bit, which is here. So your reference angle is equal to 180 degrees minus the original angle. Essentially what you're doing is you're taking 180, which is the whole half of a circle, and that sounded weird, whole half, and then you're, by subtracting off the angle, you're subtracting off this section, and it just leaves you with this wedge. That's the idea there, geometrically speaking. So when you're in quadrant 2, this is the, quote, formula, if you will, to find a reference angle. When you're in quadrant 3, so here's your terminal side, so your angle is swinging all the way across there. So something like 190 degrees or 250 degrees. It's between 180 and 270. So the reference angle, does it go here or here? Which one? We're supposed to swing from an x-axis. This would be swinging from a y-axis, so it's wrong. Your reference angle goes right here. There's your theta prime. So the idea before was we subtracted off the angle to leave us with the rest from those two things basically being supplementary angles. These two are not in that kind of position. The way you find theta prime this time is, this chunk is 180 degrees, so you're going to take the entire angle, you will take the entire angle here, and then you would subtract off the 180 degrees. So you take this bigger one and you subtract the smaller one, and that would leave you with this. So it's going to be the actual angle minus 180 degrees. And now you're probably annoyed because these two things are opposite of each other for when they're in quadrant 2 or 3. I'm going to give you an easy way to do this after we're done, per usual. All right, when you're in quadrant 4, now you're swinging almost all the way around. So that's our theta, the big go around, between 270 and 360 degrees specifically. So our reference angle is not here, it's not here, it's not there. That's swinging from the y-axis. It's here, swinging from the x-axis. That's our reference angle. It's Pac-Man sideways, kind of. So how do we find that? Well, here's the idea. If we kept going all the way around, this would be 360 degrees. This is going to feel like the first one. Let's subtract off the original angle, and that would leave us with this chunk. So the reference angle this time, I'm going to put it above, because that's where the room is, would be 360 degrees minus the original angle. I have a typo somewhere. Sorry for this. Please, eyes on my mouse. This was a typo. Your reference angle was supposed to be the original angle minus 180, not the reference angle. That was a typo. I said it right, but I wrote it wrong. I think I said it right. I hope I said it right. So make sure you get this correction right here. When you're in quadrant 3, to find a reference angle, you take the original angle and subtract off 180 degrees. All right, so one of these versions, you're doing 180 minus the angle. Another one, you're doing the angle minus 180. Another one, you're doing 360 minus the angle. You're never doing the angle minus 360. That would actually be to find coterminal angles, which you could call a coterminal angle or reference angle if it ends up in the appropriate size, but it doesn't always. So here is a sheet for this. Just take your angle and subtract 180 or 360 in an order that gives you a positive answer between 0 and 90 degrees. This will be the reference angle. How do you know whether to use 360 or 180? Whichever it's closer to. How do you know whether you should do 180 minus the angle or the angle minus 180? If you do it in one order and you get a negative, that means you did it the opposite way. Just do it the other way. Or you can even just say, all right, well, if it's negative one way, it's positive the other, and just delete the negative. Reference angles should be positive. And again, this is how I do it. I look at the number, and in my head, I'll say, all right, I need to subtract 180 because it gives me an answer between 0 and 90. Or I'll say I need to do 180 minus the original angle because that gives me an answer between 0 and 90. Or I'll say I need to do 360 minus the answer because that gives me an answer between 0 and 90. If I've gone more than full circle, then I'd go the angle minus 360 because that would give me an answer between 0 and 90 if we were in quadrant 1 still. So I really do think what I typed out is extremely helpful because it's a trial and error process, and it's not like it's an extreme case of trial and error like factoring. It's just subtract a number in 180. If that gives you something between 0 and 90, you're good. If it's negative, delete the negative. If it gave you something too large, then switch your 180 to a 360. But some people like blatant memorization of formulas and ideas, so you have the method up there for them. So for example 3, let's find the reference angle. Reference angle, third time's the charm, right? Reference angle, typing is hard. Remember, reference angles are going to be theta prime. You have got to get in good habits of labeling these appropriately. I know I'm a hypocrite since I accidentally put a dash there earlier and didn't mean to. But it is important to understand the distinction between an actual angle and a reference angle. All right. For A, we're going to start with 150 degrees. And these could be in radians as well. Spoilers for a later problem. So let's see, if I did this angle minus 180, I would get negative 30. So it's definitely not that. 150 is in quadrant 2, so it's definitely 180 minus the angle. And if you do 180 minus 150, you get 30 degrees. That's an answer that we expect. So that's the reference angle. You just got to get an answer between 0 and 90 by adding or subtracting 180 or 360. Generally not adding, but you could see some weird examples where it is. Let's do another. How about 300 degrees? So maybe you start out trying to do 180 minus this. It's going to be negative, definitely wrong. Swap it. Maybe you do 300 minus 180. So I'm going to write something that I'll erase in a second. 300 minus 180 would be 120. That's too big, man. Sorry, I was watching BoJack the other day. So if that's too big, that's not the way to do it. If it's too big, that means we probably need to switch it out to the 360. If you do 300 minus 360, it's negative, so it's definitely 360 minus 300. That'll give us our reference angle of 60 degrees. So an actual angle of 300 degrees, that was weird. An actual angle of 300 degrees is a reference angle of 60 degrees. C. Let's go with 225 degrees. And by the way, both of these 150 and 300 we'll see over and over and over and over and over. All right, 225. If I do 180 minus 225, negative, so that's not right. Swap the order. How about 225 minus 180? And if you tried 360, it would be too big. 225 minus 180 is 45. Bingo, that's in the window, so that's our reference angle. Oops. Finally, D, 7 pi over 3. Oh, radians, everybody's favorite. If you need to convert this to degrees, you would multiply by 180 degrees over pi. I'm not going to show you that. If you want to do it that way, that's your own prerogative. You do you. If you can get the answer right ultimately and get the reference angle, that's fine. But your reference angle is going to need to be in radians since it started in radians. Now 7 pi over 3, that's a pretty big number in terms of radians. In fact, I think this has gone more than full circle. So note that 2 pi over 3, I'm sorry, why did I do over 3? That 2 pi is the same thing as 6 pi over 3, just getting an LCD. 2 pi over 1 is 6 pi over 3, multiplying the top and bottom by 3, or saying 1 goes into 3, 3 times 2 is 6, however you do it. That 7's a little ugly. Let me just clean that up. 7, that is just bad. The pi is what's causing the problem. There we go, 7 pi over 3. 7's bigger than 6, which means this has gone more than full circle. So this problem is actually none of the written down cases, but I did verbalize it because we have gone 360 and then some more. We've actually gone another pi over 3, in fact, as we will see. So what we need to do is first find a coterminal angle which means we need to subtract 360. So we got to take 7 pi over 3 and subtract 360 degrees, which is 2 pi radians. But we know that 2 pi over 1 is 6 pi over 3. 7 minus 6 is 1. So that's 1 pi over 3, writing it to be meticulous for the moment. Pi over 3 is between 0 and 90 degrees. If you don't trust that, multiply by 180 over pi and you will get 60 degrees. Something that I mentioned you should memorize, in my opinion. So pi over 3 is 60 degrees, so we're in the right window. That's our reference angle. So we actually subtracted 360 to get that because this was more of a coterminal situation than quadrant 1, 2, or I'm sorry, 2, 3, or 4 to find your reference angle. So your reference angle is just coterminal, and again, without the 1 written, pi over 3. Do it that way. Now, if you left this in radians, how do you know this is between 0 and 90? Well, 90 degrees is pi over 2. Pi over 3 is smaller than pi over 2. It's got a smaller denominator. All right, now we're ready for big boy problems, big girl problems. Example 4. Evaluate the trig functions. A, we're going to have the sine of 120 degrees. We did the sine of 30 and 45 and 60 last class in 5.2. Number 5.3, we're opening up to the full circle, all 360 degrees, all 2 pi radians, not just between 0 and 90, not stuck in a right triangle. But when we're using these bigger angles, we like to reference right triangles because things like 30, 60, 45 are all in here. So if we can take something like 120 degrees and turn it into 45 or 30 or 60 as a reference angle, then we can very easily do the opposites, hypotenuses, adjacents, and their ratios as appropriate. We just might need to throw in an extra minus sign somewhere depending on the quadrant we're in. That's what we're boiling this all down to. So this stuff right here, these 2 triangles, as well as the smart trig class, is going to be necessary for what we're about to do. First thing we got to do is find the reference angle first. Find the reference angle first. If you needed to draw this up, be my guest. That's what some people like to do. So we go 120 degrees would be in quadrant 2. So this right here is our, I'll label it in red just for emphasis, 120 degrees. That's our angle. So that was theta. Theta prime would be this segment right here. So this would be the reference angle because we're swinging to the terminal side from a positive x-axis. Again, if you swung this way, you're using the y-axis, and you don't ever use the y-axis to swing from for reference angles. So this looks like the 180 minus situation. If you try to do 120 minus 180, you'd get a negative answer. All right, so theta prime will be 180 degrees minus 120 degrees, which is 60 degrees. That's our reference angle. So what we can say is that the sine of 120 degrees should be exactly the same thing as the sine of 60 degrees, but plus or minus. Not both of them, it's one or the other. That's why I'm writing the or word to distinguish it from that quadratic formula idea. It's one of these 2 things based on the original quadrant. Since our original angle, that's original angle, not the reference angle, was in quadrant 2, and we're taking a sine, quadrant 2 we're going up, that's the y value, so the sine should be positive. So this is equal to, I'll write the plus for emphasis for now, positive sine of 60 degrees. And again, this is what other students want to do. They want to rush. They don't want to think about, oh, the quadrant makes it positive or negative. They'll just say sine of 120 is positive sine of 60. They just say that they're equal. But again, this aspect will make or break you over and over and over and over and over and over. You cannot forget that. How do we do the sine of 60 degrees? Well, we got to go back to our reference triangles. I'm not going to draw it up over and over and over. Here's the 30, 60, 90 triangle, which is the 1, 2, square root of 3 triangle. 1 is opposite the 30 degrees, square root of 3 is opposite the 60 degrees. I've already had a couple students emailing me about this, which one's supposed to be opposite, why am I getting these ratios backwards? We're not on the 30 degrees, we're here, we're 60 degrees, which for us right now makes the square root of 3 the opposite, that's opposite, let me spell it out, and the 2 is the hypotenuse either way. The 1 is the adjacent. We're doing a sine, so we need opposite over hypotenuse. So that would be the square root of 3 over the 2. You should probably draw these triangles over and over and over. Even though I'm not doing it inside of the problem, I've referenced it. Draw that up yourself. So this will be equal to, positive, I'm not going to write the plus sign anymore, the square root of 3 over 2. Again, where did the square root of 3 and the 2 come from? They came from the 30, 60, 90 triangle right here, where the square root of 3 was opposite the 60, the 2 is the hypotenuse. Square root's in the top, so that's perfectly fine. This is one of my favorite types of trig problems. I love these to death. You will see them in very numerous on the first test. You'll see it constantly throughout the semester. Trigonometry is all about balance. It's all about understanding that all of this stuff is related to each other. Quite honestly, trigonometry has like 6 types of problems to it, but we just do them in so many different ways and from so many different approaches. Hey, let's do it when we're in the first quadrant only. Now let's extend it to all the quadrants. Hey, let's do this idea, then let's extend that idea. So tangent of 135. So let's find the reference angle first. So let's draw up that stuff again. So 135, that's still going to put us in quadrant 2. You have got to know your quadrants based on degrees. So this is our theta, which is 135 degrees, which means our reference angle is going to be this small wedge again. There's our theta prime. So theta prime should be 180 degrees minus 120 degrees, which is going to be 45 degrees. Why did I write 20? 135. Where did the 20 come from? 135 degrees, and that's 45 degrees. I think I was looking right here when I said it. So our reference angle is 45 degrees. So the trig function at 135 degrees is the same as the trig function of 45 degrees, but plus or minus, maybe positive, maybe negative. We will have to establish that. So the tangent of 135 degrees is maybe positive, maybe negative. We'll establish that in a second. The tangent of 45 degrees. All their coordinates, their opposites, adjacents, hypotenuses, all the same. It's just based on the quadrant, maybe it's a negative answer instead ultimately. So since our original angle is in quadrant 2, that makes the tangent, is it positive or negative? We're in quadrant 2. Tangent is the ratio of y over x if you're thinking about it that way. Y is positive, x is negative, so that ratio would be negative. If you did a smart trig class, A is quadrant 1, S is quadrant 2, that says sine is the only positive thing in quadrant 2 out of sine, cosine, and tangent. Remember, the reciprocal functions share plus or minus aspects. So that also would tell us tangent's negative. So the tangent of 135 degrees is equal to the negative of the tangent of 45 degrees specifically. So we need the triangle that has 45 degrees in it. So we load it up, we redraw it. If we feel the need, you probably should feel the need to redraw that 45, 45, 90 triangle, which is right here. Draw these things until you have them memorized. Draw these things until you're absolutely getting the 30 and 60 and 90 and 1, 2, square root of 3 all in the correct positions. Because if you make this page when you start your test, as soon as you start your test and you swap the 30 and 60, you're going to get a ton of answers wrong if you do everything else appropriate to it. All right, so tangent of 45, TOA, opposite over adjacent. Opposite's 1, adjacent's 1, so the tangent's 1 over 1, which is 1. I'll be specific for now. Opposite was 1, adjacent was 1, but we have the negative because of being in a different quadrant, which makes this whole thing equal to negative 1. We might actually not finish this section today. Wow. It's a long section, to be fair. Oops, wrong color. C. Next, let's do the cosine of 330 degrees. So let's find our reference angle first, so we can go to the side and drop our quadrants. And if you don't have to do this drawing, then you don't have to. Like I said, some of you will just play with let's add or subtract 180. Nah, those numbers are going to be too big or negative. Let's try 360. Well, if you did 360 minus 330, you'd get 30. There you go. There's your reference angle. And you could say, oh, I know 330 is in quadrant 4. But again, some of you will need to draw this up. This would be 330 degrees, roughly. That's our actual angle, which makes this tiny little chunk our reference angle. And that would be found, the only way to get an answer between 0 and 90 is to do 360 minus 330, the original angle, which would be 30 degrees. That is our reference angle. So that says the cosine, the cosine of 330 degrees should be the exact same thing as the cosine of 30 degrees, but maybe positive, maybe negative. We're going to have to figure that out next. All right, so since we're in quadrant 4, wrong color, since the original angle is in quadrant 4, that says the cosine is, let's see, cosine is the x value. Quadrant 4 means we're going right, so it's positive. Or a smart trig class, so the fourth one is quadrant 4, ASTC, that says cosine's positive in quadrant 4. I don't care which method you're using. If you have some third method that works for you, that always works, use that. So cosine of 330 degrees should be equal to the positive version of cosine of 30 degrees. How do we find the cosine of 30 degrees? We go back to those two triangles. One of them is 45, 45, so that's not it. We need the 30, 60, 90. So we go to the 30, 60, 90 triangle over here. So this is our angle this time, which makes the 1 the opposite, the square root of 3 the adjacent, and the 2 the hypotenuse. Cosine is COA, C-A-H. Well, I don't know why I said COA. Please pardon me there. I was looking at the TOA part. C-H-CA, C-A-H, adjacent over hypotenuse. So it's going to be the square root of 3 over the 2. Square root of 3 over 2. So it's the positive square root of 3 over 2. But I'm not going to write the positive sign anymore. Please don't write positive signs in your answers in my math lab. It'll probably mark it wrong. And nobody wants that. Nobody wants to have a right answer and it's wrong because you wrote a plus sign. That's just silly, right? All right, last one of these, and let's mix it up. The cosecant of 240 degrees. Actually, before that, I want to point out, look at the answers to A and C. The sine of 120 is the same as the cosine of 330, square root of 3 over 2, square root of 3 over 2. There are tons of trig functions that have the same outputs. because they're the same as the sine of 60 degrees or the cosine of 30 degrees. So the cosine of 30 is the same as the sine of 60, is the same as the cosine of 330, is the same as the sine of 120. That is why I cannot stand blatant memorization of the unit circle. There's too many overlapping answers. There's too much room to make a simple error in a plus or a minus or a square root somewhere. All right, so 240, where's that put us? Well, 180 is the quadrant breaker for 2 to 3, so this must be in quadrant 3. So our angle has to be down here somewhere. So here's the true angle theta, and that's the 240 degrees. But we need our reference angle to be this little slice right here, not the bottom one. That would swing to the y-axis. So there's our reference angle. And 240 degrees, we got to play with 180 to get an answer. If we do 180 minus 240, it'll be negative. So we go 240 minus 180, which will give us 60 degrees. That's our reference angle. So the cosecant of 240 degrees will be the same thing as the cosecant of 60 degrees, with the exception of maybe it's positive, maybe it's negative. Well, since our angle is in quadrant 3, cosecant is it positive or negative? Well, you might say, well, a smart trig class has nothing to do with cosecant, and I'd say it does implicitly, because cosecant and sine are reciprocals of each other, sin, sine. Cosecant and sin are reciprocals of each other, so if sine's positive, cosecant's positive. If sine's negative, cosecant's negative. So we're going to use a smart trig class based on sine. In quadrant 3, sine is negative, and that's because we're going down. If the sine's negative, the cosecant's negative. So cosecant is negative. So we're going to choose the minus for this one. So the cosecant of 240 degrees would be the negative cosecant of 60 degrees. Now, some of you may go ahead and switch this to being 1 over sine of 60 degrees, and that's fine. But let's actually try and remember the relationship between cosecant and its opposites, adjacents, and hypotenuses. So as a reminder, cosecant, if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. So we got to go to the 60-degree reference triangle. So we're up here this time, and cosecant is going to be hypotenuse over opposite. So hypotenuse over opposite. That'll be 2 over square root of 3. So this will be negative. I'll stop changing the color after a second. Negative 2, again, that was the hypotenuse over the square root of 3, which was the opposite. The 1 was the adjacent in reference to 60 degrees. But this is not okay because we have a square root in the bottom. I'm going to switch to an orange. So we multiply top and bottom by square root of 3. Giving us for a final answer, negative 2 square root of 3, not final, one more step, over the square root of 9, which is negative 2 square root of 3 over 3. That's our answer. If you miss that negative sign, this is completely wrong. And the funny thing is, I don't even know that it warrants partial credit because so many students, I know they're just missing half of the entire problem. Yeah, you understood the relationship between opposites and hypotenuses and adjacents, but you completely disregarded a smart trig class, the fact that you're positive or negative for different trig functions in different quadrants. So I know a lot of students want to be really upset with me if they wrote this as a positive, my math lab marks it completely wrong on a test, and then I don't give any partial credit. I really, really, really don't think you deserve a lot of partial credit for that. Maybe a point. Because all of those concepts are tied together. All right, we only have like 4 minutes left. The next example is going to take more than that, so I don't want to start an example and not finish it. So we will go ahead and end today. We will continue 5.3 next class, so on Monday. And long section establishing lots of things, so I wanted to take a lot of time to do that. But please remember that 5.2 we did finish a week ago, so that is due today by midnight. So 5.3, you can go ahead and start working on it, and I highly suggest that you go ahead and start working on the homework from 5.3, but I will not make you have to submit it until we'll finish it next class, which is the 14th, which means it'll be due on the 21st. So you've got quite a lot of time to get that 5.3 done, but remember, do it sooner than later. That way you're ready to work on 5.4 and 5.5, et cetera, et cetera. All right, so if there's no more questions, have a good day, have a good weekend, work hard on 5.2 and 5.3. We'll see you on Monday. Take care, everybody.